Один космический телевизор.
Thank you for the introduction. Actually, I will be talking of the main part of the talk, main part of the approach to quantum gravity and our recent result. And then at the end, a little few slides, I will speak about classical theorem and non-canonical theorems and quantum field theory. The talk is based on our three papers. My paper, this one, which is under publication, and our paper on which we are working is Ayam Trivedi. Ayam Trivedi is a student from Ahmedabad University, and he came now PhD at Vanderbilt University in the United States. He will have supervisor from Vanderbilt and one supervisor from Princeton. We brought together an essay to the competition, Gravitational Foundation Essay in Gravitation, and it's now on archive. So it's called The Old Problem with Cosmological Constant Solved. I will later in the talk, I will speak about applications to the cosmology. And I had in my past talks, I had quotes from Fritz Feynman and Albert Schweitzer, but now today change. I read the autobiography of Arnold Schwarzenegger. It's very interesting, from the governor of California, who is saying that we need television. I want to tell you about my vision in cosmology. So for what is good quantum gravity, that what will help us in cosmology, and this will be the main part of the talk. So in cosmology today, there are many problems, but the most urgent thing is that we know that approximately 5% of the energy content of the universe, we know that it's made from baryonic matter. We say in the cosmology, baryonic matter, which is made from not only baryons, but protons, neutrons, electrons, and simply quarks and leptons, and this we call baryonic matter. So, I mean, simply the table of unitary particle table is what we know. It's 5%. It's not too much, and we are not surprised that we don't know everything. For example, the dark matter. 27%, we are starting from what we are composed of, so we are not surprised that we don't know everything. But what is surprising that 68% is so-called dark energy. And in 2022, I attended the conference where also Roger Penrose took which was also a presentation there. It was online, and he said a very interesting thing that dark energy is not dark and it's not energy. Why? Because it is actually it's transparent. It's invisibly transparent here around us, and it's not energy. Why it's not energy? Because approximately 5 billion years in the past, the universe started to accelerate. So if we have acceleration, we need some force. We need something pumping and pumping energy to the system. So it's not in the like casual energy. So this is what he meant, and this is exactly like that. And why we are actually why I'm interested in this, that we claim that the problem of dark energy will be connected, in our opinion, from the problem of quantum gravity. So it's the hyperaccelerated expansion of the universe as a quantum phenomenon. Because I'm speaking to mathematical community, I want to just say a few words that I mean we are searching in physics. We are searching for the quantum gravity and must reduce in certain limit to quantum theory and general relativity. And today we have many approaches to quantum gravity. The most well-known is string theory. String theory brought us a new phenomenology. It's very interesting that we have brains, we have extra dimensions, closed string theory, open string theory, and it's a very rich theory. But the basic problem in string theory is that it does not solve these problems in cosmology, which are very urgent, and it is a late-time accelerated expansion of the universe. So, and this is connected with the problem of the cosmological constant. And it was my motivation already in around 2014 when I started to work on this, that what could be wrong with string theory when it does not describe the problems in cosmology which what we need to solve, the late-time cosmic acceleration. So there I have also other approaches like quantum gravity started to be developed in 1990s. Causal set approach based on the result of Stephen Hawking and David Malamud. It's a quite old approach, but the causal set approach, the kinematics is well developed, but the dynamics is still missing a lot. And it's interesting that in causal set approach there are some trials how to model the cosmological constant. I'm mentioning it from the reason that not all this list, not all these approaches are relevant for us for the reason that they are contradictory, some of them. For example, if string theory is the correct approach to quantum gravity, then causal set approach is definitely wrong. If causal set approach is the correct approach to quantum gravity, then it makes sense to do string theory, but in some sense, from the mathematical point of view, or different communities are working in the world on different approaches, and the main community is the string theory. And now I want to tell you a story about approach to quantum gravity, which is based on these articles, which is called the ring paradigm. I just want to warn you that because the ring has nothing to do with mathematical structure. It's because I defined the theory on a 1+1 dimensional grid, so like on a ring. So it has nothing to do with mathematics, but very interesting mathematics hidden behind. So now I will start to tell you a few ideas about this ring paradigm. So I defined the theory on discrete grid. So all particles and fields are attached to these rings, and so this set is known from loop quantum gravity, but we use it in different contexts. And we will do two tricks simultaneously. That we define a new phenomenological object, which is not a particle or field, and we break the assumption that the velocity of light is the highest velocity how the information is transmitted in the universe. So break the Lorentz invariance. So I will later comment it. What does it mean to break the Lorentz invariance? So the idea here is that we have particle like the train, and first the ring is put. First nature creates this ring, and later the particle is traveling on this on this ring. So so we claim that on the full non-perturbative level of physics, there are no gravitons, no casual gravitons like jumping around the objects. But first the ring is created, on which is later traveling the elementary particle. So the basic idea is that the ring is created in very short time, like in the Planck time, is decaying to these graviton phonons, and it means that between the objects, I mean, there is to spread some matter in between some matter between the casual matter in the universe. So in some sense, if I would explain, if you know the history, how general relativity was created, so people before that speak about ether in physics, and in some sense we are returning to the idea of ether, but in the case of gravitons, not photons. So I use in this construction that I simply quantize the vibration of the grid of matter in the universe, and I obtain their phonons, okay? And so I don't change. So we start the theory, I mean, like in the symmetries of string theory, but we simply model graviton differently. So the model of graviton is on full non-perturbative level. It's modeled different, and the computations with phonons is, I have a toy model here for you, that there are sitting galaxies in the universe, are sitting galaxies, and I quantize the vibration of this grid. So for this, it's necessary that the identification. If you look to the books, how about quantum electrodynamics, how we model photons as ladder operators in quantum electrodynamics, then they have very similar form how phonons have in statistical physics. And the phonons have very interesting analogical properties as gravitons. So at least at the first look at this identification, you obtain how we did the calculation concerning the Newtonian limit. And I want now to show you two immediate results. When we formulated the theory and we did the first calculation concerning the graviton phonons, then we have two immediate results. So first of all, we have some. I'm a member also of the LISA collaboration. In the LISA collaboration, we are studying how quickly the gravitational waves are traveling. And the gravitational waves are today, we have very good bounds that the gravitational waves are traveling almost. We have bounds almost this velocity of light, but it's built in general relativity. It's like it's velocity of light. But now we see from the quantum gravity perspective how why it should be exactly c, right? Not almost exactly c, and this is interesting. And this other thing is the similarity. I was always asking why the Newton and Coulomb law has the similar form. Why there's any reason why they should have at the trivial level why they should have the similar form. And now we see why there is some deep duality between gravity theories and electromagnetism. I will later comment. Okay. Now I will just I will explain why this problematics solves gives us first hints how to solve the old problem of the cosmological constant, which was my first motivation why to develop this formalism. And actually, if you know the basics of general relativity, and you can say that these are Einstein equations. Yes, I will say yes, but with only one exception, that the lambda r is a cosmological constant. But it's here, it is computed from quantum field theory. It means that it has the value which we expect from quantum field theory. And the CG is some higher velocity than the velocity of light. So this is the reason, this is the result that we break the Lorentz invariance. And this, so shortly at the beginning of cosmological inflation, so as we have the graph standard Big Bang model, so time zero, some bang, something at the beginning, cosmological inflation, and late time accelerated expansion. So 5 billion years in the past, late time accelerated expansion, and cosmological inflation 10 to the minus 43 seconds to 10 to the minus 32 seconds after the Big Bang. So we are now in the time 10 to the minus 43 seconds after the Big Bang. And the correct field equations look like this. So very quickly, this gravitational ring decays, and they change to these
equations.
And later, it's a cosmological picture. Later in the universe, we need this gravitational ring is beginning to discuss some scalar field, which is phantom field, and then cosmological constant, some effective cosmological constant appeared approximately 5 billion years in the past. So the basic picture which we have in our mind is that the gravitational rings are breaking on megaparsec distances approximately. So how the universe was expanding, the gravitational rings start to break at least approximately 5 billion years in the past. So why this is interesting? There are several reasons why it will have wide application in physics and also to the mathematical community. I will say a few words about the mathematical things. So first of all, the singularity theorems. The singularity theorems of Stephen Hawking and Roger Penrose celebrated singularity theorems because under very general assumptions, the singularities like the black holes forms in the universe, and they have some assumptions, and it means that because this theory is non-singular, it means that some assumptions in these theorems must be violated. So this will be one area of the applications. Other thing is, and my interest is that we already started to think about new project and that about work how to build cosmological inflation inside a cyclic model of the universe. I don't know if you know if you heard about cyclic model of Paul Steinhardt and Neil Turok. It's a result from 2001, and this model says that the universe is going from Big Bang, it's expanding, then accelerated expansion, and then again collapsing to big crash. So in trillion years, these cycles are appearing in the universe, and they exactly need the phantom fields. And the phantom fields are it's very interesting. The phantom fields are connected with superluminal signaling. So this will be also very interesting. Black hole information paradox, of course, is of interest because if information is traveling superluminally in the universe, it means that shortly before the radiation array of the black hole, the information is traveling out superluminally from the black hole. So and other interesting things. Also from curvature, dimensional reduction, curvature of the universe, and of course determinism of physical theories, because the ring is first created, on which is later traveling the algebraic particle. So when you hear in the physical community about Lorentz breaking theories, people usually are wondering how we want to solve the basic problems in Lorentz breaking. But there are two basic problems that we experimentally know that Lorentz symmetry is not broken, that we know that we have very good balance on the velocity of gravitons. But much more interesting thing is from the theoretical point of view is that, or other interesting thing is that breaking of the Lorentz invariance in the high energy sector will necessarily leads to evaluation of Lorentz symmetry in the low energy sector. So this theory is a result of Alexandre Perez from Marseille, and so it means if when we have experimental bounds that the Lorentz symmetry is not broken, that then how we want to succeed. But both of the issues could be answered inside the ring paradigm. The reason is that the graviton phonons are traveling exactly with velocity of light. So there is no violation of this velocity. And the second thing that the first point, concerning the first point, we use such a transformations that looks like very similar as Lorentz transformation, but with higher velocity CG. And this now I come to, I want to put a few slides only about the mathematical things, because this all would be just interesting fairy tale if there is not given some mathematics behind it. And the mathematics, I want to say a few words about the Coleman-Mandel theorem. That it was 60s, 70s. It was these are no-go theorems, which very vacuously tells me that how the Lorentz group should be embedded in some bigger group. So no-go says that it's not possible to embed something bigger. But the half-proportional symmetry theorem is the let's go theorem, which was used for supersymmetry. And I recently started. I contacted one mathematician in Madrid that concerning interesting paper where it is possible to generalize the graded super algebras to colored algebras and the algebras of the order F. So we are trying to generalize the high-proportional theorem, because if this quantum was claiming in quantum gravity would be true, then it would mean that these theorems must be generalized. And from pure mathematical point of view, I mean, generalization is I don't need to tell you the reason why to generalize the theorem. So here I have the basic definition of the colored superalgebras, and I need to say that already in this article there is written that there is an isomorphism between the colored superalgebras and the graded superalgebras, which means that that we are not interested in this generalizations, but we are much more interested in generalization of the superalgebras of the order of F. So here's the definition, and this it must fulfill this commutation relation. So this is cyclic commutation relation. So if this would be confirmed, ring paradigm, we say paradigm from the point of view that it's in a very early stage of development. So if it would be confirmed, it would have one day very interesting applications applications to astrobiology and to communication on big distances, because today we know that we can communicate on big distances. For example, the distance Sun Earth is in minutes, so just in fraction of seconds, and this will be very interesting. And I want to say that there are three big impulses to modern physics: that the phantom fields concerning the cyclic model of the universe. So the phantom field cosmology is a very interesting area of research people developing, and as I said, the phantom fields have very interesting properties. No-go theorems is for the mathematical community, and the third area of research is that Gaussian and Weyl double copy. It's a very actively developing area of theoretical physics. So there are some dualities on the level of exact solutions between gauge theories and gauge gravity theories, and we claim much more. There's not only duality on the level of exact solutions, but that there is some duality on the full non-perturbative level of physics. The last slide, I want to just, when I was talking about at the beginning about vision. So this is our vision in physics, and I want to show one sad slide, but I will continue with a very optimistic slide. This is from internet. Where our colleagues are not able to work from some reason hard because of some problems with government or some war lines, war zones, and I believe that new technologies will bring us quantum gravity will bring peace on Earth, and there is much to do on the Earth that we want to see new results in physics, mathematics. We want to see very beautiful artistic works. We want to